Hey folks, now that I've found my feet with the channel, so to speak, I'm going to start on creating a thematic series regarding the geological history of the Earth and other things in the future. I'm going to read the overview of the Eon, then the period, then moving on to more specific readings of eras and going over the major events of each era. The one exception will be, in today's video, the Hadean era, as this is not broken down into periods as of yet, as it happened at the very beginning of Earth's history, so it's not very well known, even to the scientists who study it. Instead, I'm going to speak about the Hadean era itself, the formation of the Moon, which happened in that era, and the formation of some of the oldest rock formations still around found to date. Right before I start with the Hadean period, however, or era, I'm going to read a general geological history of Earth and how it formed. I hope you enjoy it. The geological history of Earth follows the major events in the Earth's past, based on a geological timescale, a system of chronological measurement based on the study of the planet's rock layers, stratigraphy. Earth formed about 4.54 billion years ago by accretion from the solar nebula, a disc-shaped mass of dust and gas left over from the formation of the Sun, which also created the rest of the solar system. Earth was initially molten due to extreme volcanism and frequent collisions with other bodies. Eventually, the outer layer of the planet cooled to form a solid crust when water began accumulating in the atmosphere. The Moon formed soon afterwards, possibly as a result of the impact of a planetoid with the Earth. Outgassing and volcanic activity produced the primordial atmosphere. Condensing water vapor, augmented by ice delivered from comets, produced the oceans. However, more recently, in August 2020, researchers reported that sufficient water to fill the oceans may have always been on the Earth since the beginning of the planet's formation. As the surface continually reshaped itself over hundreds of millions of years, continents formed and broke apart. They migrated across the surface, occasionally combining to form a supercontinent. Roughly 750 million years ago, the earliest known supercontinent, Rodinia, began to break apart. The continents later recombined to form Pangaea, 600 to 540 million years ago, then finally Pangaea, which broke apart 200 million years ago. The present pattern of ice ages began about 400 million years ago, then intensified at the end of the Pliocene. The polar regions have since undergone repeated cycles of glaciation and thaw, repeating every 40,000 to 100,000 years. The last glacial period of the current ice age ended about 10,000 years ago. The Precambrian includes approximately 90% of geologic time. It extends from 4.6 billion years ago to the beginning of the Cambrian Period, about 541 million years ago. It includes 3 eons, the Hadean, Archean, and Phanerozoic. Major volcanic events altering the Earth's environment and causing extinctions may have occurred at least 10 times in the past 3 billion years. The Haitian Eon. During Hadean time, 4.6 to 4 billion years ago, the solar system was forming, possibly within a large cloud of gas and dust around the Sun, called an accretion disk, from which the Earth formed 4 6,500 million years ago. The Hadean Eon is not formally recognized, but it essentially marks the era before we have an adequate record of significant solid rocks. The oldest dated zircons date from about 4,400 million years ago. Earth was initially molten due to extreme volcanism and frequent collisions with other bodies. Eventually the outer layer of the planet cooled to form a solid crust when water began accumulating in the atmosphere. The Moon formed soon afterwards, possibly as a result of the impact of a large planetoid with the Earth. Some of this object's mass merged with the Earth, significantly altering its internal composition, and a portion was ejected into space. Some of the materials survived to form an orbiting moon. More recent potassium isotopic studies suggest that the moon was formed by a smaller, high-energy, high-angular momentum giant impact, leaving off a significant portion of the Earth. Outgassing of volcanic activity produced the primordial atmosphere. Condensing water vapor, augmented by ice delivered from comets, produced the oceans. However, more recently, in August 2020, researchers reported that sufficient water to fill the oceans may have always been on Earth since the beginning of the planet's formation. During the Hadean, the late heavy bombardment occurred approximately 4,100 to 3,800 million years ago, during which a large number of impact craters are believed to have formed on the Moon, and by inference on Earth, Mercury, Venus, and Mars as well. Archean Eon. The Earth of the early Archean, 4,000 to 2,500 million years ago, may have had a different tectonic style. During this time, the Earth's crust cooled enough that rocks and continental plates began to form. Some scientists think because the Earth was hotter, that plate tectonic activity was more vigorous than it is today, resulting in a much greater rate of recycling of crustal material. This may have prevented cratonization and continent formation until the mantle cooled and convection slowed down. Others argue that the subcontinental lithosphere mantle is too buoyant to subduct, and that the lack of Archean rocks is a function of erosion and subsequent tectonic events. In contrast to the Proterozoic, Archean rocks are often heavily metamorphized deep-water sediments, such as grey rocks, mudstones, volcanic sediments, and banded iron formations. Greenstone belts are typical Archean formations, consisting of alternating high and low-grade metamorphic rocks. The high-grade rocks were derived from volcanic island arcs, while the low-grade metamorphic rocks represent deep-sea sediments eroded from the neighboring island rocks and deposited in a four-arc basin. In short, greenstone belts represent sutured protocontinents. The Earth's magnetic field was established 3.5 billion years ago. The solar wind flux was about 100 times the value of the modern Sun, so the presence of the magnetic field helped prevent the planet's atmosphere from being stripped away, which is probably what happened to the atmosphere of Mars. However, the field strength was lower than at present, and the magnetosphere was about half the modern radius. Phanerozoic Eon. The geologic record of the Phanerozoic, 2,500 to 541 million years ago, is more complete than that for the preceding Archean. In contrast to the deep water deposits of the Archean, the Proterozoic features many strata that were laid down in extensive shallow epicontinental seas. Furthermore, many of these rocks are less metamorphosed than Archean age ones, and plenty are unaltered. Study of these rocks showed that the Eon featured massive, rapid continental accretion, unique to the Proterozoic supercontinent cycles, and wholly modern orogenic activity. Roughly 750 million years ago, the earliest known supercontinent, Rodinia, began to break apart. The continents later recombined to form Pangaea 600 to 540 million years ago. The first known glaciations occurred during the Proterozoic. One began shortly after the beginning of the Eon, while there were at least 4 during the Neo-Proterozoic, climaxing with the symbol Earth of the Varangian Glaciation. Phanerozoic. The Phanerozoic Eon is the current Eon in the geologic timescale. It covers roughly 541 million years. During this period, continents drifted about, eventually collected into a single landmass known as Pangaea, and then split up into the current continental landmasses. The Phanerozoic is divided into 3 eras: the Paleozoic, the Mesozoic, and the Cenozoic. Most of the evolution of multicellular life occurred during this time period. The Paleozoic era. The Paleozoic spanned from roughly 542 to 251 million years ago, and is subdivided into 6 geologic periods. From oldest to youngest, they are the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian. Geologically, the Paleozoic starts shortly after the breakup of a supercontinent called Pangaea, and at the end of a global ice age. Throughout the earlier Paleozoic, the Earth's landmass was broken up into a substantial number of relatively small continents. Towards the end of the era, the continents gathered together into a supercontinent called Pangaea, which included most of Earth's land area. Cambrian Period. The Cambrian is a major division of the geologic timescale that begins about 541 plus or minus a million years. The Cambrian continents are thought to have resulted from a breakup of a Neoproterozoic supercontinent called Pangaea. The waters of the Cambrian period appear to have been widespread and shallow. Continental drift rates may have been anomalously high. Laurentia, Baltica, and Siberia remained independent continents following the breakup of the supercontinent of Pangaea. Gondwana started to drift towards the South Pole. Panthalassa covered most of the southern hemisphere, and minor oceans included the Paleo Teflocion, the Subdivisions, and Canti Ocean. Ordovician Period. The Ordovician period started at a major extinction event called the Cambrian Ordovician Extinction Event, sometime about 485.4 plus or minus 1.9 million years ago. During the Ordovician, the southern continents were collected into a single continent called Gondwana. Gondwana started the period in the equatorial latitudes and, as the period progressed, drifted towards the South Pole. Early in the Ordovician, the continents Laurentia, Siberia, and Baltica were still independent continents since the breakup of the supercontinent Pangaea earlier, but Baltica began to move towards Laurentia later in the period, causing the Subdivisions to shrink between them. Also, Avalonia broke free from Gondwana and began to head north towards Laurentia. The Rhaetic Ocean was formed as a result of this. By the end of the period, Gondwana had neared or approached the pole and was largely glaciated. The Ordovician came close in a series of extinction events that, taken together, comprise the second largest of the 5 major extinctions in Earth's history in terms of percentage of genera that became extinct. The only larger one was the Permian Triassic extinction event. The extinctions occurred approximately 447 to 444 million years ago and mark the boundary between the Ordovician and the following Silurian period. The most commonly accepted theory is that these events were triggered by the onset of an ice age and the Hadean faunal stage, the end of the long, stable greenhouse conditions typical of the Ordovician. The ice age was probably not as long-lasting as once thought. Study of oxygen isotopes in fossil brachiopods shows that it was probably no longer than 0.5 to 1.5 million years. The event was preceded by a fall in atmospheric carbon dioxide from 7,000 parts per million to 4,400 parts per million, which selectively affected the shallow seas where most organisms lived. As the southern supercontinent Gondwana drifted over the South Pole, ice caps formed on it. Evidence of these ice caps have been detected in the other Ordovician rock strata of North Africa and then adjacent northeastern South America, which were South Polar locations at the time. Silurian Period. The Silurian is a major division of the geologic timescale that started about 443.8 plus or minus 1.5 million years ago. During the Silurian, Gondwana continued a slow southward drift to high southern latitudes, but there is evidence that the Silurian ice caps were less extensive than those of the late Ordovician glaciation. The melting of ice caps and glaciers contributed to a rise in sea levels, recognizable from the fact that Silurian sediments overlie eroded Ordovician sediments, forming an unconformity. Other cratons and continent fragments drifted together near the equator, starting the formation of a second supercontinent, known as Euramerica. The vast continent of Panthalassa covered most of the northern hemisphere. The other minor oceans include Prototethys, Paleo Tethys, the Rhaetic Ocean, a seaway of the Iapetus Ocean, now in between Avalonia and Laurentia, and the newly formed Ural Ocean. Devonian Period. The Devonian spanned roughly from 419 to 359 million years ago. The period was a time of great tectonic activity as Laurasia and Gondwana drew closer together. The continent Euramerica, or Laurasia, was created in the early Devonian by the collision of Laurentia and Baltica, which rotated into the natural dry zone along the Tropic of Capricorn. In these near deserts, the old red sandstone sedimentary beds formed, made red by the oxidized iron hematite, characteristic of drought conditions. Near the equator, Pangaea began to consolidate from the plates containing North America and Europe, further raising the northern Appalachian Mountains and forming the Caledonian Mountains in Great Britain and Scandinavia. The southern continents remained tied together in the supercontinent of Gondwana. The remainder of modern Eurasia lay in the northern hemisphere. Sea levels were higher worldwide, and much of the land lay submerged under shallow seas. The deep, enormous Panthalassa, the universal ocean, covered the rest of the planet. Other minor oceans were Paleo Tethys, Prototethys, Rhaetic Ocean, and Ural Ocean, which was closed during the collision with Siberia and Baltica. Carboniferous Period. A global drop in sea level at the end of the Devonian reversed early in the Carboniferous. This created the widespread epicontinental seas and carbonate deposition of the Mississippian. There was also a drop in south polar temperatures. Southern Gondwana was glaciated throughout the period, though it is uncertain if the ice sheets were a holdover from the Devonian or not. These conditions apparently had little effect in the deep tropics, where lush coal swamps flourished within 30 degrees of the northernmost glaciers. A mid-Carboniferous drop in sea level precipitated a major marine extinction, one that hit crinoids and ammonites especially hard. This sea level drop and the associated unconformity in North America separated the Mississippian period from the Pennsylvanian period. The Carboniferous was a time of active mountain building, as the supercontinent Pangaea came together. The southern continents remained tied together, and the supercontinent Gondwana, which collided with North America, Europe, Laurasia, along the present line of eastern North America. This continental collision resulted in Haitian orogeny in Europe, along the Alleghenian orogeny in North America. It also extended the newly uplifted Appalachian southwestward as the Ouachita Mountains. In the same time frame, much of the present Eastern Eurasian plate welded itself to Europe along the line of the Ural Mountains. There were two major oceans in the Carboniferous, the Pangaea and the Paleo Teflocion. Other minor oceans were shrinking and eventually closed. The Red Ocean, closed by assembly of North and South America, the small, shallow Ural Ocean, which was closed by the collision of Baltica and Siberia continents, creating the Ural Mountains, and the Proto-Tethys Ocean. Permian Period. During the Permian, all the Earth's major land masses, except portions of East Asia, were collected into a single supercontinent known as Pangaea. Pangaea straddled the equator and extended towards the poles, with a corresponding effect on ocean currents in the single great ocean, Pangaea, the universal sea. The Paleo Tethys Ocean, a large ocean that was between Asia and Gondwana. This Sumeria continent rifted away from Gondwana and drifted north to Laurasia, causing the Paleo Tethys to shrink. A new ocean was growing on its southern end, the Tethys Ocean, an ocean that would dominate much of the Mesozoic era. Large continental land masses create climates with extreme variations of heat and cold, continental climate, and monsoon conditions with highly seasonal rainfall patterns. Deserts seem to have been widespread on Pangaea. Mesozoic era. The Mesozoic extended roughly from 252 to 66 million years ago. After the vigorous convergent plate mountain building of the late Paleozoic, the Mesozoic tectonic deformation was comparatively mild. Nevertheless, the era featured the dramatic rifting of the supercontinent Pangaea. Pangaea gradually split into the northern continent, Laurasia, and the southern continent, Gondwana. This created the passive continental margin that characterizes most of the Atlantic coastline, such as along the United States East Coast today. The Triassic Period. The Triassic Period extends from about 252.17 plus or minus 0.06 to 201.3 plus or minus 0.2 million years ago. During the Triassic, almost all the Earth's land mass was concentrated into a single supercontinent, centered more or less on the equator, called Pangaea, or meaning all the land. This took the form of a giant They took the form of a giant Pac-Man with an east-facing mouth, constituting the Tethys Sea, a vast gulf that opened further westward in the mid-Triassic, at the expense of the shrinking Paleo-Teflocion, an ocean that existed during the Paleozoic. The remainder was the world ocean known as Panthalassa, or the sea. All the deep ocean sediments laid down during the Triassic have disappeared through subduction of oceanic plates. Thus very little is known of the Triassic open ocean. The supercontinent Pangaea was rifting during the Triassic, especially late in the period. It had not yet separated. The first non-marine sediments in the rift that marked the initial breakup of Pangaea was separated New Jersey from Morocco, are of late Triassic age. In the US, these thick sediments comprise the Newark supergroup. Because of the limited shoreline of one supercontinental mass, Triassic marine deposits are globally relatively rare, despite their prominence in Western Europe, where the Triassic was first studied. In North America, for example, marine deposits are limited to a few exposures in the West. Thus, Triassic stratigraphy is mostly based on organisms living in lagoons and hypersaline environments, such as Etheria crustaceans and terrestrial vertebrates. Jurassic Period. The Jurassic Period extends from about 201.3 plus or minus 0.2 to 145 million years ago. During the early Jurassic, the supercontinent Pangaea broke up into the northern supercontinent Laurasia and the southern supercontinent Gondwana. The Gulf of Mexico opened in the new rift between North America and what is now Mexico's Yucatan Peninsula. The Jurassic North Atlantic Ocean was relatively narrow, while the South Atlantic did not open until the following Cretaceous Period, when Gondwana itself rifted apart. The Tethys Sea closed, and the Neo-Tethys Basin appeared. Climates were warm, with no evidence of glaciation. As in the Triassic, there was apparently no land near either pole, and no extensive ice caps existed. The Jurassic geological record is good in Western Europe, where extensive marine sequences indicate a time when much of the continent was submerged under shallow tropical seas. Famous locales include the Jurassic West Coast World Heritage Site and the renowned late Jurassic Lagerstätten of Holzmarden and Sohnhofen. In contrast, the North American Jurassic record is the poorest of the Mesozoic, with few outcrops at the surface. Though the epicontinental Sundance Sea left marine deposits in parts of the northern plains of the United States and Canada during the late Jurassic, most exposed sediments from this period are continental, such as the alluvial deposits of the Morrison Formation. The first of several massive batholiths were emplaced in the northern Cordillera, beginning in the mid-Jurassic, marking the Nevadan orogeny. Important Jurassic exposures are also found in Russia, India, South America, Japan, Australasia, and the United Kingdom. Cretaceous Period. The Cretaceous Period extends from circa 145 million years ago to 66 million years ago. During the Cretaceous, the late Paleozoic, early Mesozoic supercontinent of Pangaea completed its breakup into present-day continents, although their positions were substantially different at the time. As the Atlantic Ocean widened, the convergent margin orogenies that had begun during the Jurassic continued in the North American Cordillera, as the Nevadan orogeny was followed by the Sevier and Laramide orogenies. Though Gondwana was still intact at the beginning of the Cretaceous, Gondwana itself broke up as South America, Antarctica, and Australia rifted away from Africa, though India and Madagascar remained attached to each other. Thus the South Atlantic and Indian Oceans were newly formed. Such active rifting lifted great undersea mountain chains along the welts, raising eustatic sea levels worldwide. To the north of Africa, the Tethys Sea continued to narrow. Broad shallow seas advanced across central North America, the Western Interior Seaway, and Europe then receded late in the period, leaving thick marine deposits sandwiched between coal beds. As a side note, this Western Interior Seaway is actually where the majority of America's oil comes from. I'd highly suggest looking up. It is super interesting. Although if anyone's interested, I could do a reading for you too. At the peak of the Cretaceous transgression, 1/3 of Earth's present land area was submerged. The Cretaceous is justly famous for its chalk. Indeed, more chalk formed in the Cretaceous than any other period in the Phanerozoic. Mid-ocean ridge activity, or rather the circulation of seawater through the enlarged ridges, enriched the oceans in calcium. This made the oceans more saturated, as well as increased the bioavailability of the element for calcareous nanoplankton. These widespread carbonates and other sedimentary deposits make the Cretaceous rock record especially fine. Famous formations from North America include the rich marine fossils of Kansas' Smoky Hill chalk member and the terrestrial fauna of the late Cretaceous Hell Creek Formation. Other important Cretaceous exposures occur in Europe and China. In the area that is now India, massive lava beds called the Deccan Traps were laid down in the very late Cretaceous and early Paleocene. Cenozoic era. The Cenozoic era covers 66 million years since the Cretaceous Paleogene extinction event up to and including the present day. By the end of the Mesozoic era, the continents have drifted into nearly the present form. Eurasia became North America and Eurasia, while Gondwana split into South America, Africa, Australia, Antarctica, and the Indian subcontinent, which collided with the Asian plate. This impact gave rise to the Himalayas. The Tethys Sea, which had separated the northern continents from Africa and India, began to close up, forming the Mediterranean Sea. Paleogene Period. The Paleogene Period is a unit of geologic time that began 66 and ended 23.03 million years ago, and comprises the first part of the Cenozoic era. This period consists of the Paleocene, Eocene, and Oligocene epochs. Paleocene Epoch. The Paleocene lasted from 66 million years ago to 56 million years ago. In many ways, the Paleocene continued processes that had begun during the late Cretaceous period. During the Paleocene, the continents continued to drift towards their present positions. The supercontinent Laurasia had not yet separated into 3 continents. Europe and Greenland were still connected. North America and Asia were still intermittently joined by a land bridge, while Greenland and North America were beginning to separate. The Laramide orogeny of the late Cretaceous continued to uplift the Rocky Mountains in the American West, which ended in the succeeding epoch. North and South America remained separated by equatorial seas. They joined during the Neogene. The components of the former southern supercontinent Gondwana continued to split apart, with Africa, South America, Antarctica, and Australia pulling away from each other. Africa was heading towards Europe, slowly closing the Tethys Ocean, and India began its migration to Asia that would lead to a tectonic collision and the formation of the Himalayas. Eocene Epoch. During the Eocene, 56 million years ago to 33.9 million years ago, the continents continued to drift towards their present positions. At the beginning of the period, Australia and Antarctica remained connected, and warm equatorial currents mixed with colder Antarctic waters, distributing the heat around the world and keeping global temperatures high. But when Australia split from the southern continent around 45 million years ago, the warm equatorial currents were deflected away from Antarctica, and an isolated cold water channel developed between the two continents. The Antarctic region cooled down, and the ocean surrounding Antarctica began to freeze, sending cold water and ice flows north, reinforcing the cooling. The present pattern of ice ages began about 40 million years ago. The northern continent of Laurasia began to break up as Europe, Greenland, and North America drifted apart. In western North America, mountain building started in the Eocene, and huge lakes formed in the high flat basins among uplifts. In Europe, the Tethys Sea finally vanished, while the uplift of the Alps isolated its final remnant, the Mediterranean, and created another shallow sea with island archipelagos in the north. Though the North Atlantic was opening, a land connection appears to have remained between North America and Europe, since the faunas of the two regions are very similar. India continued its journey away from Africa and began its collision with Asia, creating the Himalayan orogeny. Oligocene Epoch. The Oligocene Epoch extends from about 34 million years ago to 23 million years ago. During the Oligocene, the continents continued to drift towards their present positions. Antarctica continued to become more isolated and finally developed a permanent ice cap. Mountain building in western North America continued, and the Alps started to rise in Europe as the African plate continued to push north into the Eurasian plate, isolating the remnants of the Tethys Sea. A brief marine incursion marks the early Oligocene in Europe. There appears to have been a land bridge in the early Oligocene between North America and Europe, since the faunas of the two regions are very similar. During the Oligocene, South America was finally detached from Antarctica and drifted north towards North America. It also allowed the Antarctic circumpolar current to flow, rapidly cooling the continent. Neogene Period. The Neogene Period is a unit of geologic time starting 23.03 million years ago and ends at 2.588 million years ago. The Neogene Period follows the Paleogene Period. The Neogene consists of the Miocene and Pliocene and is followed by the Quaternary Period. Miocene Epoch. The Miocene extends from about 23.03 to 5.333 million years ago. During the Miocene, continents continued to drift towards their present positions. Of the modern geologic features, only the land bridge between South America and North America was absent. The subduction zone along the Pacific Ocean margin of South America caused the rise of the Andes and the southward extension of the Mesoamerican Peninsula. India continued to collide with Asia. The Tethys Seaway continued to shrink and then disappeared as Africa collided with Eurasia and the Turkish-Arabian region between 19 and 12 million years ago, according to ICS 2004. Subsequent uplift of mountains in the western Mediterranean region and global fall in sea levels combined to cause a temporary drying up of the Mediterranean Sea, resulting in the Messinian salinity crisis near the end of the Miocene. Pliocene Epoch. The Pliocene extends from 5.333 million years ago to 2.58 million years ago. During the Pliocene, continents continued to drift towards their present positions, moving positions possibly as far as 250 kilometers, 155 miles, from their present locations to positions only 70 kilometers from their current locations. South America became linked to North America through the Isthmus of Panama during the Pliocene, bringing a nearly complete end to South America's distinctive marsupial faunas. The formation of the isthmus had major consequences on global temperatures, since the warm equatorial ocean currents were cut off, and an Atlantic cooling cycle began, with cold Arctic and Antarctic waters dropping temperatures in the now isolated Atlantic Ocean. Africa's collision with Europe formed the Mediterranean Sea, cutting off the remnants of the Tethys Ocean. Sea level changes exposed the land bridge between Alaska and Asia. Near the end of the Pliocene, about 2.58 million years ago, the start of the Quaternary Period, the current ice age began. The polar regions have since undergone repeated cycles of glaciation and thaw, repeating every 40 to 100,000 years. The Quaternary Period. And there's nothing written specifically for the Quaternary Period, so we'll move to the Plasticine Epoch. The Pleistocene extends from 2.588 million years ago to 11,700 years before present. The modern continents were essentially at their present positions during the Pleistocene, and the plates upon which they sit probably have moved no more than 100 kilometers, or 62 miles, relative to each other since the beginning of the period. Holocene Epoch. Current Earth. The Holocene Epoch began approximately 11,700 calendar years before present, and continues to the present. During the Holocene, continental motions have been less than a kilometer. The latest glacial period of the current ice age ended about 10,000 years ago. Ice melt caused world sea levels to rise about 35 meters or 115 feet in the early part of the Holocene. In addition, many areas above 40 degrees north latitude have been depressed by the weight of the Pleistocene glaciers and rose as much as 180 meters or 591 feet over the late Pleistocene and Holocene, and are still rising today. The sea level rise and temporary land depression allowed temporary marine incursions into areas that are now far from the sea. Holocene marine fossils are known from Vermont, Quebec, Ontario, and Michigan. Other than higher latitude temporary marine incursions associated with glacial depression, Holocene fossils are found primarily in lake bed, floodplain, and cave deposits. Holocene marine deposits along low latitude coastlines are rare because the rise in sea levels during these periods exceeds any likely upthrusting of non-glacial origin. Post-glacial rebound in Scandinavia resulted in the emergence of coastal areas around the Baltic Sea, including much of Finland. The region continues to rise, still causing weak earthquakes across northern Europe. The equivalent event in North America was a rebound of the Hudson Bay, as it shrank from its larger, immediate post-glacial Tyrrell Sea phase to near its present boundaries. And that concludes the short geologic history of Earth. And now we begin on the specific eras, starting with the Hadean era. The Hadean is a geologic eon of Earth's history preceding the Archean that began with the formation of the Earth about 4.6 billion years ago and ended, as defined by the International Commission on Stratigraphy, the ICS, 4 billion years ago. As of 2016, the ICS describes its status as informal. The term was coined after the Greek mythical underworld Hades by American geologist Preston Cloud, originally to label the period before the earliest known rocks on Earth. W. Brian Harland later coined an almost synonymous term, the Priscoan period, from priscus, the Latin word for ancient. Other older texts refer to the eon as the pre-Archean. Hadean, from Hades, the Greek god of the underworld and the underworld itself, describes the hellish conditions then prevailing on Earth. The planet had just formed and was still very hot, owing to its recent accretion, the abundance of short-lived radioactive elements, and frequent collisions with other solar system bodies. Subdivisions. Since few geologic traces of this eon remain on Earth, there is no official subdivision. However, the lunar geologic timescale embraces several major divisions relating to the Hadean, so these are sometimes used in an informal sense to refer to the same periods of time on Earth. The pre-Nectarian, from the formation of the Moon's crust 4,533 million years ago, up to about 3,920 million years ago, and the Nectarian, ranging from 3,920 million years ago up to about 3,850 million years ago, in a time when the late heavy bombardment, according to that theory, was declining. In 2010, an alternative scale was proposed that includes the addition of the Chaosian, the Prenophallian, and Prenophallian eons preceding the Hadean, and divides the Hadean into three areas with 2 periods each. The Paleo-Hadrian era consists of the Hephaestion, 4.5 to 4.4 billion years ago, and the Jacobean periods, 4.4 to 4.3 billion years ago. The Meso-Hadean is divided into the Canadian, there's an insult there, I know it, 4.3 to 4.2 billion years ago, and the Procrustean periods, 4.2 to 4.1 billion years ago. The Neo-Hadean is divided into the Acastan, 4.1 to 4 billion years ago, and the Promethean periods, 4 to 3.9 billion years ago. As of February 2017, this has not been adopted by the IUGS. Hadean rocks. In the last decades of the 20th century, geologists identified a few Hadean rocks from western Greenland, northwestern Canada, and western Australia. In 2015, traces of carbon minerals interpreted as remains of biotic life were found in 4.1 billion year old rocks of Western Australia. On a side note, that's only a little way away from me. If you're interested in these rocks, you can look up Shark Bay on the coast of Western Australia. And if you look on a map from the southwestern tip where you find Cape Leeuwin, if you go a bit above a third of the way up, about 400 or 500 kilometres north of Geraldton, you'll see Shark Bay with its two prominent peninsulas. The oldest dated zircon crystals, enclosed in a metamorphosed sandstone conglomerate in the Jack Hills of the Naria Nest terrain of Western Australia, date 4.404 plus or minus 0.008 billion years ago. This zircon is a slight outlier, with the oldest consistently dated zircon falling closer to 4.35 billion years ago, around 200 million years after the hypothesized time of the Earth's formation. In many other areas, xenocrest or rollicked Hadean zircons enclosed in older rocks indicate that younger rocks have formed on older terrains and have incorporated some of the older material. One example occurs in the Guiana Shield from the Iwakrama Formation of southern Guyana, where zircon cores have been dated at 4.22 billion years ago. A sizable quantity of water would have been in the material that formed the Earth. Water molecules would have escaped Earth's gravity more easily when it was less massive during its formation. Hydrogen and helium are expected to continually escape, even to the present day, due to atmospheric escape. Part of the ancient planet is theorized to have been disrupted by the impact that created the Moon, which should have caused melting of one or two large regions of the Earth. Earth's present composition suggests that there was not complete remelting, as it is difficult to completely melt and mix huge rock masses. However, a fair fraction of material should have been vaporized by this impact, creating a rock vapor atmosphere around the young planet. The rock vapor would have condensed within 2,000 years, leaving behind hot volatiles, which probably resulted in a heavy carbon dioxide atmosphere with hydrogen and water vapor. Liquid water oceans existed despite the surface temperature of 230 Celsius, 446 Fahrenheit, because at an atmospheric pressure of above 27 atmospheres, caused by the heavy carbon dioxide atmosphere, water is still liquid. As cooling continued, subduction and dissolving in ocean water removed most carbon dioxide from the atmosphere, but the level still oscillated wildly as new surface mantle cycles appeared. Studies of zircons have found that liquid water must have existed as long ago as 4.4 billion years ago, very soon after the formation of the Earth. This requires the presence of an atmosphere. The cool early Earth theory covers a range from about 4.4 to 4.1 billion years ago. A September 2008 study of zircons found that the Australian Hadean rock holds minerals pointing to the existence of plate tectonics as early as 4 billion years ago, approximately 600 million years after the Earth's formation. If this is true, the time when Earth finished its transition from having a hot molten surface and the atmosphere full of carbon dioxide to being very much like it is today can be roughly dated to about 4 billion years ago. The action of plate tectonics and oceans trapped vast amounts of carbon dioxide, thereby reducing the greenhouse effect and leading to a much cooler surface temperature and formation of solid rock, possibly even life. Lunar divisions. The lunar genealogical timescale, or selenological timescale, divides the history of Earth's moon into 5 generally recognized periods: the Copernican, Eratosthenian, Embryon, late and early, Nectarian, and pre-Nectarian. The boundaries of this timescale are related to large impact events that have modified the lunar surface, changes in crater formation through time, and the size-frequency distribution of craters superposed on geological units. The absolute ages for these periods have been constrained by radiometric dating of samples obtained from the lunar surface. However, there is still much debate concerning the ages of certain key events, because correlating lunar regolith samples with geological units on the moon is difficult, and most lunar radiometric ages have been highly affected by an intense history of bombardment. The primary geological processes that have modified the lunar surface are impact cratering and volcanism, and by using standard stratigraphic principles, such as the law of superposition, it is possible to order these geologic events in time. It was thought that the mere basalts might represent a single stratigraphic unit with a unique age, but it is now recognized that mere volcanism was an ongoing process, beginning as early as 4.2 billion years ago, and continuing to perhaps as late as 1.2 billion years ago. Impact events are by far the most useful for defining lunar stratigraphy, as they are numerous and form in the geological instant. The continued effects of impact cratering over long periods of time modify the morphology of lunar landforms in a quantitative way, and the state of erosion of a landform can also be used to assign a relative age. The lunar geological timescale has been divided into 5 periods, successively pre-Nectarian, Nectarian, Embryon, Eratosthenian, and Copernican, with one of these, the Embryon, being subdivided into 2 epochs, early and late. These divisions of geological time are based on the recognition of convenient geomorphological markers, and as such, they should not be taken to imply that any fundamental changes in geological processes have occurred at these boundaries. The Moon is unique in the solar system in that it is the only body other than the Earth for which we possess rock samples with a known geological context. By correlating the ages of samples obtained from the Apollo missions to known geological units, it has been possible to assign absolute ages to some of these geological periods. The timeline below in this article represents one such attempt, but it is important to note, as discussed, that some of the ages are either uncertain or disputed. In many lunar highland regions, it is not possible to distinguish between Nectarian and pre-Nectarian minerals or materials, and these deposits are sometimes labelled as just pre-Embryon. Pre-Nectarian. The pre-Nectarian period of the lunar geologic timescale runs from 4.533 billion years ago, the time of the initial formation of the Moon, to 3.92 billion years ago, when the Nectaris Basin was formed by a large impact. It is followed by the Nectarian Period. Pre-Nectarian rocks are rare in the lunar sample suite. They are mostly composed of lunar highlands material, which have been heavily churned, brachiated, and thermally affected by subsequent impacts, particularly during the heavy bombardment Eon, HBE, a period of 0.61 billion years from the formation of the Moon until at least the formation of the Embryon Basin 3.9 billion years ago, or even later with the formation of the Orientalis Basin that marks the approximate beginning of the Nectarian Period. The primary pre-Nectarian lunar highland material is dominated by the rock type anorthosite, which suggests that the early stage of lunar crustal formation occurred via mineral crystallization of a global magma ocean. This geologic period has been informally subdivided into the cryptic era 4.533 to a 4.172 billion years ago, and basic groups 1 to 9, 4.172 to 3.92 billion years ago. But these divisions are not used on any geologic maps. Since little or no geological evidence on Earth exists from the time spanned by the pre-Nectarian period of the Moon, the pre-Nectarian has been used as a guide by at least one notable scientific work to subdivide the unofficial terrestrial Hadean Eon. In particular, it is sometimes found that the Hadean Eon is subdivided into the cryptic era basins groups 1 to 9, Nectarian and Lower Embryon, though the first two of these lunar divisions are informal and collectively make up the pre-Nectarian. Nectarian. The Nectarian period of the lunar geologic timescale runs from 3,920 million years ago to 3,850 million years ago. It is the period during which the Nectaris Basin and other major basins were formed by large impact events. The ejecta from Nectaris form the upper part of this densely cratered terrain found in lunar highlands. Since little or no geological evidence on Earth exists from the time spanned by the Nectarian period of the Moon, the Nectarian has been used by at least one notable scientific work as an unofficial subdivision of the terrestrial Hadean Eon. Embryon. The Embryon is a lunar geologic period divided by two epochs, the early Embryon and the late Embryon. In the lunar geologic timescale, the early Embryon epoch occurred between 3,850 million years ago to about 3,800 million years ago. It overlaps the end of the late heavy bombardment in the inner solar system. The impact that created the huge Mare Embryon Basin occurred at the start of the epoch. The other large basins that dominate the lunar near side, such as Crisium, Tranquillitatis, Serenitatis, Fecunditatis, and Procellarum were also formed in this period. The basins filled with basalt mostly during the subsequent late Embryon epoch. The early Embryon was preceded by the Nectarian. Since little or no geological evidence on Earth exists from the time spanned by the early Embryon epoch of the Moon, the early Embryon has been used by at least one notable scientific work as an unofficial subdivision of the terrestrial Hadean Eon. In the lunar geologic timescale, the late Embryon epoch occurred between 3,800 million years ago to about 3,200 million years ago. It was the epoch during which the mantle below the lunar basins partially melted and then filled with basalt. The melting is thought to have occurred because of the impact of the early Embryon thinned the overlying rock, either causing the mantle to rise because of reduced pressure on it, bringing the molten material closer to the surface, or the top melting as heat flowed upwards through the mantle because of reduced overlying thermal insulation. The majority of lunar samples returned to Earth for study come from this epoch. The Earth equivalent consists of about half the Archean Eon. Eratosthenian Period. The Eratosthenian Period in the lunar geologic timescale runs from about 3,200 million years ago to 1,100 million years ago. It is named after the crater Eratosthenes, which displays characteristics typical of craters of this age, including a surface that is not significantly eroded by subsequent impacts, but which also does not possess a ray system. The massive basaltic volcanism of the Cambrian Period tapered off and ceased during this long span of lunar time. The youngest lunar lava flows identified from orbital images are tentatively placed near the end of this period. Its Earth equivalent consists of most of the Meso-Archean and the Archean eras, Archean Eon, Paleo Proterozoic and Mesoproterozoic eras, the Proterozoic Eon. Copernican Period. The Copernican Period in the lunar geologic timescale runs from approximately 1.1 billion years ago to the present day. The base of the Copernican Period is defined by the impact craters that possess bright, optically immature ray systems. The crater Copernicus is a prominent example of a ray crater, but does not mark the base of the Copernican Period. Copernican age deposits were mostly represented by crater ejecta, but a small area of mere basalt has covered a part of, and is thus younger than, some of the rays of the Copernican crater Lichtenberg, and therefore the basalt is mapped as Copernican age. And that's the end of the lunar division. Now onto a more detailed page of the oldest dated rocks on Earth. The oldest dated rocks formed on Earth as an aggregate of minerals that have not been subsequently broken down by erosion or melted, and are more than 4 billion years old, formed during the Hadean era of Earth's geological history. Meteorites that were formed in other solar systems can predate the Earth. Particles from the Murchison meteorite were dated in January 2020 to be 7 billion years old. Hadean rocks are exposed on the Earth's surface in very few places, such as in the geologic shields of Canada, Australia, and Africa. The ages of these felsic rocks are generally between 2.5 and 3.8 billion years. The approximate ages have a margin of error of millions of years. In 1999, the oldest known rock on Earth was dated to 4.031 plus or minus 0.003 billion years, and is part of the Acasta Ness of the Slave Craton in northwest Canada. Researchers at McGill University found a rock with a very old model age for extraction from the mantle, 3.8 to 4.28 billion years ago. I'm going to try this, but I'm going to probably brutalize it. Novogotic greenstone belt on the coast of Hudson Bay in northern Quebec, and if I did mess that up, I am sorry. The true age of these samples is still under debate, as they may actually be closer to 3.8 billion years old. Older than these rocks are crystals of the mineral zircon, which can survive the disaggregation of the parent rock and be found in dated and younger rock formations. In January 2019, NASA scientists reported the discovery of the oldest known Earth rock on the Moon. Apollo 14 astronauts returned several rocks from the Moon, and later, scientists determined that a fragment from a rock named Big Bertha, which had been chosen by astronaut Alan Shepard, contained a bit of Earth from about 4 billion years ago. The rock fragment contained quartz, feldspar, and zircon, all common on the Earth but highly uncommon on the Moon. In January 2020, astronomers reported that the oldest mineral on Earth so far are Murchison meteorite particles. They have been determined to be 7 billion years old, billions of years older than the 4.54 billion years age of the Earth itself. The oldest material of terrestrial origin that has been dated is the zircon mineral of 4.404 plus or minus 0.008 billion years, enclosed in a metamorphosed sandstone conglomerate in the Jack Hills of the Nile terrain of Western Australia. The 4.404 plus or minus 0.008 billion years old ago zircon is a slight outlier, with the oldest consistently dated zircon falling closer to 4.35 billion years. The zircon is a part of a population of zircons within the metamorphosed conglomerate, which is believed to have been deposited around 3.06 billion years ago, which is the age of the youngest detrital zircon in the rock. Recent developments in the atom probe tomography method have led to further constraint on the age of the oldest continental zircon, with the most recent age quoted as 4.374 plus or minus 0.006 billion years old. In January 2019, NASA scientists reported the discovery of the oldest known Earth rock on the Moon. I'm going to skip that because I've already read it. The oldest rock formation is, depending on the latter's research, either a part of the Isua Greenstone Belt, the Neogene terrain, the Novogotic Greenstone Belt, the Napier Complex, or the Acasta Gneiss on the Slave Craton. The difficulty in assigning the title to one particular block of gneiss is that the gneisses are all extremely deformed, and the oldest rock may be represented by only one streak of minerals, and a mylonite representing a layer of sediment or an old dike. This may be difficult to find or map, hence the oldest dates yet unresolved are as much generated by luck and sampling as by an understanding of the rocks themselves. It is thus premature to claim that any of these rocks, or indeed that of other formations of Hadean gneisses, is the oldest formations or rocks on Earth. Doubtless new analyses will continue to change our conceptions of the structure and nature of the ancient continental fragments. Nevertheless, the oldest cratons on Earth include the Cup-Val craton, the western gneiss terrain of the Yilgarn craton, 2.9 to 3.2 billion years old, the Pilbara craton, 3.4 billion years old, and portions of the Canadian Shield, 2.4 to 3.6 billion years ago, or billion years old. Part of the polystarted Dawa craton in India are greater than 3 billion years. The oldest dated rocks of the Baltic Shield are 3.5 billion years old. Other old formations include the Sagal. The Acasta Gneiss in the Canadian Shield in the Northwest Territories, Canada, is composed of the Archean gneiss and gneissic cores of ancient mountain chains that have been exposed in a glacial peneplain. Analysis of zircon from a felsic ortho gneiss with presumed granitic protolith, returned an age of 4.031 plus or minus 0.003 billion years old. On September the 25th, 2008, researchers from McGill University, Carnegie Institution for Science, and UQAM announced that a rock formation in the Nunavut Greenstone Belt, exposed on the eastern shore of Hudson Bay in northern Quebec, had a SM-TAC-ND model age for extraction from the mantle of 4.28 billion years. However, it is argued that the actual age of the formation of this rock, as opposed to the extraction of its magma from the mantle, is likely to be closer to 3.8 billion years, according to Simon Wild of the Institute for Geoscience Research in Australia. The zircons from the Western Australia Jack Hills returned an age of 4.404 billion years, interpreted to be the age of crystallization. These zircons also show another interesting feature. The oxygen isotope composition has been interpreted to indicate that more than 4.4 billion years ago, there was already water on the surface of Earth. The importance and accuracy of these interpretations is currently the subject of scientific debate. It may be that the oxygen isotopes and other compositional features, the rare earth elements, record more recent hydrothermal alterations of the zircons, rather than the composition of the magma at the time of their original crystallization. In a paper published in the journal Earth and Planetary Science Letters, a team of scientists suggests that rocky continents and liquid water existed at least 4.3 billion years ago and were subjected to heavy weathering by an acrid climate. Using an iron microprobe to analyze isotope ratios of the element lithium and zircon from the Jack Hills of Western Australia, and comparing these chemical fingerprints to lithium compositions in zircons from continental crust and primitive rocks similar to the Earth's mantle, they found evidence that the young planet already had the beginnings of continents, relatively cold temperatures, and liquid water by the time the Australian zircons formed. Meteorites, however, can be even older. In January 2020, astronomers reported that the oldest material on Earth found so far are Murchison meteorite particles, which have been determined to be 7 billion years old, 2.5 billion years older than the Sun itself, which formed about 4.56 billion years ago. One of the oldest Martian meteorites found on Earth, ALH 84001, discovered in the Allen Hills of Antarctica, has been reported to have crystallized from molten rock 4.091 billion years ago. The Genesis rock, Lunar sample 15415, obtained from the Moon by astronauts during the Apollo 15 mission, has been dated at 4.08 billion years. During Apollo 16, older rocks, including Lunar sample 67215, dated at 4.46 billion years, were brought back, and the sample known as NWA 11119 has been dated to 4.5648 plus or minus 0.0003 billion years. This concludes today's video. Thank you so much for listening. I appreciate it so much. I made a little bit of a change to speak slightly faster and to make myself a little clearer due to the quality of my microphone. It's not the greatest. After all, I want you to all possibly learn something new while you chill out and listen. So I like to be heard, well, really well. If you enjoyed the video, I would love it if you liked or subscribed or left me a comment or maybe some feedback. Thank you so very much and have a beautiful day.